Hi, everyone, and good morning. Thank you for joining us. My name is Brett Norton with Beyond Clean, and I'd like to welcome back those of you joining us for another Beyond Clean virtual event, and also would like to extend a very warm welcome to those joining us for the first time. Today's webinar is titled Power Play, Ensuring the Safety of Ultrasound Probes Through Electrical Leakage Testing. In sterile processing, we know nothing is more vital than providing safe and sterile instrumentation for the patients we serve. So how do we ensure the safety and functionality of our ultrasound probes? Levi Moore joins us to shine a spotlight on the crucial yet often overlooked step in probe reprocessing, electrical leakage testing. We'll explore the ins and outs of probe anatomy, all while demonstrating proper techniques for electrical leakage testing. I'd like to thank our event sponsor, Acertera Acoustic Laboratories, for helping make this amazing education possible. And for those of you here for CE credits, I'm sure all of you are. So just want to make sure that I point this out. The CE credit will be available after the webinar, so hang in until after the end for your CE certificate. At the conclusion of the webinar, you will automatically be directed to the CE event quiz. And once you complete that quiz, your 1CE certificate will be ready to download. If you're joining us live today, I really do encourage you to ask questions. We are here live. It's not a pre-record or anything. So Levi is here to entertain all of your questions related to the presentation. So please feel free to ask questions. A little bit of housekeeping. Since we are dealing with technology, sometimes we have issues with audio or video. So if you do have issues, please go ahead and refresh your browser. That fixes the issue probably about 99.9% of the time. We do have some new icons. They are smiley faces or emojis. So go ahead and share your reactions to the information presented during today's webinar by selecting your favorite emoji. We do have some downloadable resources provided by Acertera up in the right-hand side of your screen, so please feel free to jump in and check those out. We also have our Beyond Clean LinkedIn link, so give us a follow if you haven't already, and you can stay up to date on the latest Beyond Clean content and educational events. All right, let's get this one rolling. Joining us for the webinar event today is Levi Moore. Levi is the president and CEO of Acertera Acoustic Laboratories. He has over 15 years of associated ultrasound testing, regulatory and management experience, and is responsible for Acertera's certified ultrasound probe repair business. Levi holds multiple patents in the field of ultrasound maintenance and is a member of the NEMA, N-E-M-A, MITA, M-I-T-A, Committee on Artificial Intelligence. All right, I'll stop talking and get Levi into the studio so he can go ahead and present this great presentation. Welcome, Levi.
Thanks, Brett, and thank you for making all this possible. So I appreciate the time that everybody is spending here to get an opportunity to go over electric leakage testing. Obviously, it's quite an important safety step that is often overlooked, and I'm excited to get a chance to have a chance to actually talk with you all about that this morning. As Brett said, I have been involved in ultrasound for quite a long time. I usually say in the bio it says 15 years because most people don't believe I've been doing this for 26 years. So we definitely have been spending quite a lot of time working in ultrasound and specifically working to try to maximize the capabilities of our friends in the hospital to test and ensure safety for patients. So this presentation is going to go over the safety of ultrasound probes that we're going to look to achieve through electrical leakage testing. I may try to abbreviate that as ELT throughout the presentation, just because saying electrical leakage testing for the next 55 minutes might get a little tiresome for everybody. So this presentation, the goal is that by the end we'll have gone through and you can describe the anatomy, the cleaning and inspection of probes, proper electrical leakage testing and what you need to pay attention to in those things. Also, maybe where you can go to get additional information when you need it. As well as to state the importance of the safety of electrical leakage testing and the training and competency requirements. Give me a second here to pull this up. Excuse me. There we go. So in this presentation, we're going to have a few common terms, and so defining what those terms are so that we're all speaking the same language here. Likely, you're all familiar with many of these things, but just so that we're on the same page throughout the presentation, I'm going to go over a few of these here. TEE is what the industry calls transesophageal echocardiography probes. These are typically very expensive ultrasound probes relative to the rest of the probes that you'll see. You may or may not see in sterile processing, but you will certainly see throughout the hospital. TEE probes are similar in how they look to other endoscopes, but TEE probes have an ultrasound transducer at the end, and in those TEE probes you have the various components that we'll kind of go through, but it has an insertion tube and control housing that are going to look somewhat similar to what you would see on other endoscopes that you might be more familiar with. EBUS listed here is the endiobronchial ultrasound scopes. They're similar in that they are used to be inserted into the body to be able to image patients with a clear path to tissue. Ultrasound doesn't go through air very effectively. Ultrasound doesn't go through bone very effectively. So to be able to create the images that the physicians need to decide which therapies to apply, often imaging from inside the body is the easiest way to do that. EUS, again, is an esophageal ultrasound scope that is again, very similar to the other things that we've already discussed. Typically from the control housing, for most of the probes that we're going to be looking at, from the control housing down to the ultrasound system, there's a cable. And that cable has typically somewhere between 192 and 256 coaxial cables in there. They're really small, small enough that when I give tours at our office, I like to show people, because you can't actually even see the two wires that are in there with your naked eye. At least I can't, and most folks agree. So those very fine wires are connecting the ultrasound system to the individual elements inside of the TEE probe or the ultrasound probe. The housing of a probe, depending on the probe that you're talking about, typically surrounds the actual ultrasound array itself. It has a lens set in it, and that's true for TE probes. It's also true for standard, what I would call G&E probes, or general and endocavity probes. The ultrasound array is definitely the most sensitive part of the transducer. So it's something that you want to be very cognizant of when you're doing the electrical leakage testing, and when you're doing any sort of cleaning of the probe. That's the area that's most likely to be damaged during those processes. So you want to try to make sure that you've cared for it. It has been inspected, and there's not going to be obvious failures to come out of that before it goes into those harsh, high-level disinfecting steps. The lens is the patient contact interface. We use lens very ubiquitously in ultrasound, and many of these patient contact interfaces on probes that we call lenses, many of them are actually lenses. They help to provide focus for the ultrasound at a specific depth. And then that is adjusted when those probes are used by physicians to electrically, they can adjust that focus to be able to shift their region of interest to make sure that they're looking at the anatomy in the best detail they can get in the region that they're interested in. So sonographers and physicians are using that to do it. But some of those lenses are not actually lenses. They're not doing any focusing or anything like that, but they're meant to keep the electronics of the probe separate from the patient. They provide a nice patient interface, and typically they're doing something that is interesting to hear about, and maybe it sounds kind of complicated, but when ultrasound hits a very big impedance, acoustic impedance mismatch, you get a reflection. And that's how we make our images in ultrasound. The bigger the change in that acoustic impedance mismatch, the more of the sound is reflected, less goes into the remaining tissue or the remaining area that is in the path of that ultrasound. And that lens is typically designed to be sort of a half step between the very high acoustic impedance of the ultrasound transducer array and the lower impedance of human tissue. So by taking a smaller step, or sometimes multiple smaller steps in that acoustic impedance, you actually end up being able to deliver more power into the patient so that you can make the images that you need at the depths you need to be able to make them. I've mentioned transducer a few times, and it's easy to look at a probe and think, well, the probe and transducer are often used interchangeably. When you look at a probe and you see the actual ultrasound array that sits underneath there, it's an array. It is not. It's not just a single block of electronics or parts. In order to make those ultrasound images, there are typically somewhere between 64 up to as many as maybe 9,600 individual ultrasound crystals inside of that array. And so if you look at one of these probes, particularly a TEE probe, in a very small space, maybe a half an inch by a half an inch, you can have as many as 2,500 elements. So these elements are very, very small. Each of those elements makes up the array, and each one is effectively its own small crystal transmitter, right? And they all work on the piezoelectric effect, which is the ultrasound system will transmit an electrical signal. That electrical signal changes the shape or vibrates the crystal in the end of the ultrasound transducer. And as that crystal changes shape, it produces pressure waves, right? Sound. And that sound will travel into the body. It gets absorbed, it gets reflected, it gets attenuated as it is moving through the body. And each time reflections are sent back through a period of time, those are received by that same crystal and reinterpreted. The pressure waves come back, and they actually compress that crystal again. That compression or that change in the shape of the crystal then produces electrical signals that are interpreted by the ultrasound system as an image, right? It's a brightness, it's an intensity for a given pixel on the screen. And that is actually how they come up with, if you hear B mode imaging, it's brightness mode. It's taking the intensity of the sound that comes back and interpreting that into the intensity of a pixel at a given depth or a given location based on time. So it's kind of a neat thing to be able to look at and understand how those images are made. Typically on G&E probes, the general and endocavity probes, the probe is handled by the housing. In TEE probes, most of the housing and the insertion tube are going to be inside the patient. And so the control housing is typically where the anesthesiologist or whoever's actually using the TEE probe is going to handle that probe, and that's where there's typically buttons to be able to steer. You might see these in the image here on the left. There are buttons to be able to steer the array so that they can electronically, sometimes mechanically, shift the focus of the array. And then there's a couple of knobs on there that allow you to articulate the end of the probe, the distal tip, in two perpendicular 180-degree planes, so that you can basically manipulate it while it's inside the body to acquire the best image possible. All right, that's a lot of stuff to go through. I know it's a lot of stage to set here, but I want to make sure that we're all speaking the same language here. So let's talk about a little about probes that are in use. So I mentioned G&E probes. There's an example of an abdominal imaging probe there at the top. This probe is from Philips, but obviously this is not unique to them. Everybody makes an abdominal imaging probe, and sometimes it's the most commonly recognized use of ultrasound by the layperson is, oh, you use that to look at babies, right? Exactly. So this is the way that we start to plan pregnancies, determine gestational age, all those kinds of things, so that we can make sure that the baby's delivered and everybody gets to be really happy about how that turns out. So these types of curved linear probes are what are typically used for those types of exams. Other examples of those standard ultrasound probes would include things like a linear probe that is characterized by just having a very flat array. Those tend to be higher frequency because they're not looking for the same sort of depth. There's a relationship in ultrasound between the frequency of the probe that is doing the transmitting and the depth at which you can image. So it's 1 dB per centimeter per megahertz. And so if you look at what that means is, the higher your frequency goes, the less depth you're going to be able to get into the system, because you're going to be giving up a lot more energy for every centimeter you go into the tissue. Now, why use high frequency at all? Well, the higher the frequency, the smaller the ultrasound wave, right? So then you can resolve smaller structures, or you get better resolution in the images that you produce. So all these probes are going to be made very specifically for the application that they've been designed for. They have unique applications, unique physiology, and they're looking for unique pathology in looking at the patients. So you have this curved probe, you have a linear probe. Then other probes that you would see in G&E probes are cardiac, like phased array probes that are shaped to be able to image from outside the body. They sit into these acoustic windows between rib bones. When the scan is actually being done, they actually, it's kind of uncomfortable pressing that in between your ribs to be able to image the heart. And then finally, I would say the one that is most likely to be seen besides TEE probes in sterile processing would be endocavity probes. So that would be endovaginal and endorectal probes. And those each are characterized by kind of a long shaft with the ultrasound array at the end. They typically have what we call a very tightly curved array, and that gives the sonographer or physician a very wide field of view when they actually go to do their procedures. So those are the standard ultrasound probes, and in large categories and in broad swaths. The TEE probes that are probably a lot more common to see in sterile processing, you can see pictured here in the second image down, the middle image there. TEE probes are phased arrays. Some are capable of 3D imaging, some are not. They're typically used in planning, let's say planning valve replacements or during open heart surgeries to keep the ultrasound image available and the data available to the physician. But let's say you're doing open heart surgery. Now the ultrasound probe is down the patient's throat, and they're able to image the heart from very closely through just a small amount of tissue so that they can achieve the best image and not interfere with the surgery. And that does bring up the the importance of what we're actually looking at here, is that the TE probes are down the patient's throat, and they're in very close proximity to the patient's heart. So any electrical leakage can create some pretty substantial challenges for those patients. It's very careful. Let's see. So Jesse asked, the leakage testers for specific probes have a set limit by manufacturer. That's generally accurate, right? The TE probes are, and all probes, you have an instructions for use document that comes with those probes. They're available for anybody to download. You don't even have to own the probe. You can go do your own research to get information for those. But those instructions for use, or IFUs, they're also supposed to have in them the specific electrical leakage limits for those transducers. That may not always agree with the electric leakage tester that you're using. Some have just standard programmed values, right? It might say if you go over 175 microamps, it fails. If it's under 175 microamps, it doesn't fail. And those electric leakage testers are ubiquitous. They're used quite frequently. I tend to believe that it's better to be able to see the specific value and to be able to set the limits in your tester based on what the OEMs are telling us are the specific limits for that probe, and to be able to understand sort of where that falls in the whole range of available values. So high voltage readings are not the only concern when you're looking at electric leakage. All of, any failure is, what are we measuring when we're actually measuring electric leakage? And this is getting a little bit ahead of myself here, but you're measuring the breakdown in the insulators between the electronics and the outside of the probe. And so that breakdown can be manifested in several ways. It can be a hole in the insertion tube. It could be a hole in the articulation sleeve or bending neck rubber. It could be a hole in the tip or a crack in the tip of the probe when we're talking about TE probes. And that electric leakage itself can present a danger to the patient, but it is also the correlated dangers that are at least as important as that particular issue. And that's when you get fluid ingress into that device, you can have opportunities for cross-contamination. And more than likely, in my experience, I've been doing this 26 years, a lot of ultrasound probe repair through that time. you're going to often destroy your probe. You're going to have problems with your transducer there and cost time and money for the hospital, but also present a danger to the patient. And my approach to this whole thing, I look at the safety in ultrasound across the board. I've participated in more than 2,500 FDA 510K submissions for new ultrasound devices. The most important thing for us is that we're able to deliver excellent images and not hurt the patient, right? It might not be my mom, but it might be your mom. I want to make sure that if she has to depend on that exam, that it's being done properly, right? That it's, and I know that you all bring a lot of the same enthusiasm to the to your job. So 3 hookups to test. Yeah, I think there's a Jesse, there's a GE probe that you actually have to also ground the control housing. That's true that you'll get a passing result if you don't require all of them. But generally speaking on those, that's passing result you'll often see on older models of electric leakage testers. You're not actually testing the probe. So you're missing a critical component of that circuit to be able to actually test the probe. It's definitely a patient safety issue if you're not actually getting that information. And then I'll jump back after I answer Lorraine's question here. How often should TE probes be reprocessed? They're supposed to be after every exam, obviously. If they haven't been used, it's unlikely that you're going to see other problems. The essential flow of testing, specifically with TE probes, is that you do your initial cleaning to make sure that the patient tissue and the most of the grossness is off of it. It may not be actually sterilized or disinfected at this point. Excuse me. But once that initial cleaning has been done, before you soak it in Cydex or use automated reprocessors or soak it in any of the other approved high-level disinfecting solutions, the electric leakage testing needs to be done, because if you find a problem in electric leakage testing at that stage, you can save the hospital from destroying the probe, right? You want to actually do the testing at that stage, then you do the high level disinfection, and now if it passes, you do the high level disinfection. If it doesn't, then obviously you need to go talk to your biomed and figure out what your hospital's protocol is for the next steps to resolve that issue. So I hope that answers your question. Finally, jumping back to the slide, finally, there is endoscopic ultrasound probes, and those are endoscopes that are used to gather visual information, and then the physician actually has the option to switch over or to simultaneously acquire ultrasound images from the tissue that they're looking at. And yes, Lisa, I do recommend that the leakage test be done before the high-level disinfection. So typically, the probes get rinsed, they're going to get wiped down, so that you get the main bulk of patient material or however it's referred to off of the probe. And once that's done, once you've got your initial cleaning, that's when you want to do I would do clean, then leakage test, then disinfect. Those steps. A quick look at the anatomy of an ultrasound probe. On the left, we do have a standard probe. At the top, number one, the lens, the probe lens, the transducer lens. As I mentioned before, this is the patient contact interface. No, if you wet the probe, it won't necessarily create damage. You have to soak it in water to be able to do your electric leakage testing. So if you're cleaning the probe initially, these are generally pinprick holes or other small issues. The water getting in at that step, or the possibility of some of those disinfecting fluids getting in at that step, if you're using wipes or however you're doing it, is a minimal concern, only because we can't do anything else if the probe's not safe to handle, and safety for everybody else is really important. The damage actually occurs if you fail an electric leakage test, or the probe has one of those problems and gets fluid in, and then it gets plugged into a system and energized. And when it's energized, that's when you blow up things. So that's when problems, you turn all of your expensive electric components into smoke and light, and they don't like that. So the patient interface is the transducer lens. This is typically a softer material when you're looking at G&E probes. It's about the consistency of human tissue. It's very similar in how that feels, maybe a little stiffer. Some transducer manufacturers use actually hard lenses. That's less common today. The second piece you see there is the transducer housing. That's what people use to hold on to while they're actually doing the image. It protects the electronics inside, and it gives us a surface that is suitable to be disinfected. And these probes are also typically, they go through a high-level disinfection using a wipe. There are some automated solutions, and that's generally how it's handled. Number 3 on here, the strain relief. So that's where a lot of damage occurs in transducers. They get manhandled a lot. And as I mentioned at the beginning, there are these very fine wires inside of that cable, very fine. They're, if you look up the American wire gauge scale, they can be as small as 45, right, on that wire gauge scale. It's a very, very fine wire, like a human hair. And I don't know if you can see in the webcam, but I'm an expert on hair. So yeah, that's exactly what these wires are like. Finally, next 4 you see in the cable that I was just discussing. A lot of there's a cable sheath on the outside. That's typically a PVC material. Those will oxidize over time. They will pick up all the disinfecting solution that you put onto them, and so they tend to turn really yellow and tacky to the touch. Not great. Don't love those. That when that happens, there are service providers out there that can correct that issue for you if your probes look that way. The connector strain relief on the other end, this actually typically gets a lot less strain than the one at the transducer side. And then finally, you have the connector housing, which has typically a lot of electronics in it. It is the connection into the system. Sometimes you have multiplexing in that connector. Sometimes you have it in the head. But either way, there's typically a lot of electronics. I'm going to pick up the pace a little bit just because I know we do have quite a lot to get through. Transducer, so TE nomenclature. Number 1, that whole black portion there is the insertion tube. The insertion tube itself has depth markers every 10 centimeters. Those depth markers, as the probe is used, as the probe is disinfected, get wiped out. Many of these probes have a coating over the outside to be able to protect the thermoplastic of the insertion tube from all these harsh chemicals, but that breaks down over time. Then you start to see it failing in electric leakage. You start to see holes appearing. You'll start to see drag marks from when your hospital staff, they don't use the bite protectors that they're supposed to. So when they're pulling that out of the insertion tube out of the patient, they catch on teeth and they damage the probe. Those are things that you definitely want to look to, and the insertion tube along with the tip and number 6 there, the insertion tube sleeve, often referred to as a bending neck rubber or articulation sleeve. Those three components are the very most important to make sure they're in excellent physical condition when you're reprocessing these devices. So you can look over the whole thing. If you see obvious holes, it's a great time to stop after you've done that initial cleaning and get your biomed involved so that you don't cause other damage. To Lisa's point earlier, if we can avoid getting extra fluid inside the transducer, it's a good idea to do that. So moving quickly here, the cable's going to be similar to what you see on G&E probes. The connector and the strain is going to be similar to what you see on G&E probes. I've described the control housing a bit before. You can see the articulation knobs there. Those can get loose over time. So when you're doing an inspection, if you rotate that device and you've got to rotate it some portion of a full rotation before you start seeing the actual tip rotate, that's a good indication that that probe needs service, because you want to have a nice crisp response when you actually move those articulation knobs. And as I said, it's a two 180-degree planes that are perpendicular to one another. So the probe can move in this direction, and then it can also move in this direction. Right. So we've talked a bit about the anatomy of ultrasound probes. The image that you're looking at here is actually an ultrasound, an exposed ultrasound array. So on the right is the array. We're looking at it from the side. Sometimes those arrays actually have connectors on them, and the connector then maybe it plugs into a flex circuit that has all the wires soldered into it, and that gets plugged into the array, and that's all inside of that control housing. Let's see. So we talked a little bit about how the ultrasound probes use the piezoelectric effect to create ultrasound. So I'm not going to go over that again. But it is just important for me to reiterate, these electronics are really sensitive. They're very fragile. And so you want to be very careful with those, and inspecting the lens, the housing, the tip on a TEE probe, the lens on a TEE probe, to make sure that those are physically intact. You should know what they look like when they're good, because knowing really well what they look like when they're in great condition is going to help you to find those times when they don't look quite so good. So taking pictures when you first get the probe is an excellent way to be able to track those things. Maybe your hospital system has a way for you to store that kind of image so that you can say, oh, this is what it looked like when it showed up. How's it looking now? And being able to make good determination. Always a good practice if you can follow it. Okay. So now that we've kind of looked at probes and discussed some of those components, how do we take care of probes? What do we do there? I went through that already. Anatomy of the. Did I go the wrong way? Let's see. Nope. I guess I shouldn't have skipped that one over. So the ultrasound probes are in use throughout the facility, right? You might have quite a few in OBGYN, cardiology, radiology. They're spread throughout the hospital. They're used in musculoskeletal imaging, MSK, and they all have different requirements for how often electrical leakage testing needs to be conducted. Who conducts it? I don't know, right? If it inside your hospital on TE probes, that has to be done by law between every exam, right? Because there is a serious risk for the patient. So each time that's used, you're supposed to be doing electric leakage testing. You're supposed to be tracking that information. And I strongly recommend, if you can can get a nice device that can help you do that automatically, that's even better. To be able to track what are the specific values of that leakage test, so that you can look at that over time and ensure that that you don't wait until that probe fails to start getting people involved who could help it before that catastrophic failure. So how do you decide how the ultrasound probe will be disinfected? That's great. The IFU is definitely where we want to focus our time, but you can obviously use the Spalding classification of probes to be able to understand how that actually happens. So on intact skin, device classification is non-critical. I would say G&E probes fall into that category as well. So most general use probes are going to fall into that category for cardiology, vascular, radiology, and musculoskeletal imaging. Those are all going to be low-level disinfection, although people still do high-level disinfection on them, even though they don't need to. The mucous membrane or non-intact skin is classified as semi-critical, and so those require high-level disinfection. Now, all of those endocavity probes are supposed to be in a condom before they're used. And that should prevent, that's our belt and suspenders. That should help to keep those probes from being damaged and to help prevent cross-contamination. Even doing all of those things, we still do high-level disinfection on those probes. Again, those are the longer probes characterized by the long shaft and the tightly curved array at the end. These are endocavity probes, and those are high-level disinfected. TE probes are in exactly the same category because they're going into the esophagus. We don't actually have, typically, you don't put any sort of cover on those when they're inserted into the patient. And those require high-level disinfection by approved methods. And each vendor of ultrasound transducers is going to also let you know which sterilization, or sorry, which high-level disinfecting methods are approved for that, for their probe. And then, of course, you're all familiar, way more than I am, with all the devices that require sterilization inside the hospital. So we were kind of talking back and forth with Lisa earlier, the steps of probe reprocessing is the pre-cleaning. Once that's pre-cleaning is done, the probe is transported typically to your facility, central processing or sterile processing. And you probably have a sink exactly like this one where you're actually doing the manual cleaning to make sure that all the patient material is off of the probe. Once this step is done, then you want to do your electric leakage testing. So you do your rinsing, you make sure everything is ready to go, and then you're ready to do that ELT to make sure that the probe doesn't have hidden damage. So let me make sure I've covered everything that I was hoping to there. Manual cleaning and decontamination, rinse the device. Make sure that you remove any leftover debris and also all the chemistries used to clean. And just to keep saying it, in all the steps that you're going through, it's critical that you follow the probe manufacturer's instructions for use. They define the required steps for reprocessing and the compatible disinfection methods. And once we've gone through this initial cleaning, most of these probes require high-level disinfection that you're going to see, and so they go to that disinfection stage. Here it's, I apologize that this slide's got this out of order. I would put electric leakage testing prior to the high-level disinfection. And that is because typically that high-level disinfection, specifically for TE probes, but also for G&E probes, is that the probes are going to be soaked in a caustic material. The disinfecting solutions, as you're all aware, are kind of nasty things here. So I apologize that this is out of order here. I missed that when I was reviewing the presentation. But I would do electric leakage testing first. Make sure that that probe will pass electric leakage testing. If it doesn't, stop. Don't proceed. You have to go get the biomed involved, because if you proceed with the high-level disinfecting after you have found a probe does not pass electric leakage testing, the likelihood that you're going to destroy that probe is much, much higher. Let's see. You may see, you may have an automated disinfecting station. Typically, they're going to ask you if the probe passes electric leakage before you do the high-level disinfection. And of course, you want to record that data each time, right? It helps when we have data to be able to keep from having to deal with all the finger pointing that you might see when something does go wrong. You can show them the steps that you took in the data for the values that you got when you actually made the measurement. Some automated high-level disinfecting stations have an electric leakage tester that is attached to them, or an electrode that's built in, and you can hook up any electric leakage tester that you want to. Some are better than others, so make sure you do your homework there. Finally, once you have passed electric leakage testing, you do the high-level disinfection. You're going to dry the probe and store it. So typically that storage is done in a HEPA filtered cabinet, or in some other way that you have established inside your hospital to prevent recontamination. So hanging it in an open cart in a patient area is not a good idea. Don't do that. Looking closer at the actual TEE probe, bending rubber, articulation sleeve, this is an area you can kind of see the circled portion there in the middle. That's a hole where disinfecting fluid can get into the probe and destroy the electronics. That's a hole by which you could have cross-contamination, right? Nasty things living in there that you're going to go pass from patient to patient. So it's important to inspect this portion because it does move. That's where you're going to see failures tend to congregate, is in close proximity to that articulation sleeve or in the sleeve itself. So you can see the hole there. This is fairly obvious. I mentioned earlier tooth drags and holes. You can see on the center picture there a TEE probe tip. Those holes are all the tooth drags. Those are all areas where you should have concerns, right? It could cause failure of that probe when you test it on electric leakage, or it could be again a spot for cross-contamination. And here you can see a bite mark on the articulation sleeve. And so I mentioned earlier, if you want to stop a lot of these things from happening, bite guards, bite guards, bite guards. That's how you save money, and it's how you make life easier for everybody who's involved in the process. I know that's not your choice, but it's something that, you know, if all of us harp on it, maybe someday the physicians will listen to us. So I've mentioned TE probe damage, fluid ingress. What does that actually look like? So you can see some of the rust and contamination forming inside this TE probe tip. So many of these probes today have complex electronics in their high voltage switches called MUX chips. They might have application specific integrated circuits, ASICs, that are actually the whole brains of that particular ultrasound probe. The ultrasound system becomes more of a passive player in that transmission because it tells the probe go, and the ASIC is actually what creates the ultrasound, or forms the beam, gathers the transmit receive data, and then transmits complete data back to the ultrasound system. So these are very vulnerable to that fluid ingress. Again, as soon as it's energized, you're going to run into problems if you have fluid ingress. If you catch it before that probe gets plugged in and energized, sometimes there are services that can keep that probe from being a total loss. We can fix it so that it's not broken. That also will have an effect, the fluid ingress, on the articulation components inside that TE probe. You're gonna anything that moves, they're typically actually steel cables that they use inside, wound quite tightly like a piano wire, and they're very susceptible to a damage when fluid ingress occurs. Here at the top, you can see barely, you can just make out the 40 there for the 40 millimeter depth marker, or 4 centimeter depth marker, or 40 centimeter, apologize, it's 40 centimeters. So the entire insertion tube's about 1.5 meters, or about 1 meter long, and so the markers give you 10 centimeter marks there. So this is 40 centimeters. What you see in the image below is that there are services out there that will do a recoat and relabel on those. So they put new depth markers on, they put a new protective coating on to ensure that that probe is going to pass electrical leakage. It can resolve some of the holes and other issues that could have come up with that insertion tube. They're going to put a new articulation sleeve on it. They're going to make sure that that tip is polished. It looks really nice. There's not going to be tooth drags and all those kinds of things. That's certainly possible. So there's remediation possible if you pay attention to these things and get them back to a service provider when you find them. So on the control housing, you want to check the control housing for cracks. I mentioned earlier you want to articulate the knobs. If you don't start getting a response from the end of the TE probe, as soon as you start turning that knob, those cables will stretch. They'll get, the actual setting could come loose, and so you're going to start to see that manifest, and physicians will complain about that too. So if you can find it ahead of time, you can save some trouble. On all of these things, you're looking for holes, tears, bulges, or even areas that are discolored. You want to pay attention to, because that can be indicating that underlying material is compromised. So electric leakage, what is that, and what is the risk to the patient, right? So electric leakage is a breakdown in the insulators between the electrical signals and power that is going to the probe and the patient. So those insulators are typically your lens, your insertion tube. Those kinds of patient interface contact points are where you worry about this electric leakage going into the patient. And I have a video here. Brett said double click it. I don't know. I don't remember what I'm. Oh, here we go. The next one. Oop. I think that's playing for you guys here. So this is showing the danger of electrical leakage. So this is a cardiac probe, and the insulator's been broken down intentionally here. And now you can see like the amount of energy that's actually going through that probe can be significant and can be damaging. Usually it's not going to be that spectacular, but it can be life-threatening nonetheless. Like it's not good to have that happening. So let me see, am I on the right slide now? Okay. So understanding electric leakage and current here. Patient electric shock is not the only hazard that's related to a damaged probe. Fluid ingress due to damage to the probe can lead to further damage to the probe, and can lead to pathogens entering the probe that cannot be properly cleaned or disinfected, and that can be a source of contamination for the next patient. Identify the damage, get that equipment out of circulation and get it repaired. So why electric leakage testing is important in this is that often visual inspection, I'm sure that you guys do a great job, but electric leakage testing will find things that you don't see. You can't see the problem, that's the problem, right? Often you'll start to see worn insulators or holes that are going to be uncovered by disciplined electrical leakage testing that will not be evident to the naked eye necessarily. That internal contamination, internal corrosion, all those things lead to costly repairs, or in the worst cases that you have to actually replace that transducer, that probe. So how is it that these probes tend to fail, or what do we do that leads to those kinds of things? Using contaminated disinfectants, right? You want to look at those disinfectants and understand, all the same disciplines I'm sure that you use with other disinfecting solutions. When was it opened? How long is it good for? How many times am I allowed to use it? Making measurements when there are test strips to ensure, obviously, that the disinfecting solution is still suitable. Using non-OEM validated solutions or the improper strength of disinfectant is also area of issues. So the failing to inspect, I think we've kind of talked about some of the challenges there and why inspection is important. So sometimes the practice of cleaning or disinfecting probes was removed from the OR space and now moved down to a central cleaning area and facilities. And so we need to make sure that the people who are doing that are trained properly on how do they do the inspection and how do they do this electrical leakage testing to ensure that that is being done properly. Tap water can be a source of additional contamination. So you want to make sure that the water you're using to do your cleaning and rinsing is safe and clean. And then, of course, cleaning probes and then storing them improperly is a big no-no. You're going to end up with damaged probes in that way as well. So let's see, a quick review. If you look at material, published material on these items, it is possible to get bacterial infections after TE intubation. It's just something that occurs. So you can see the quote here on the slide. If you do get those those contaminated probes into people, you can get infections in the bloodstream or bacteremia. Organisms can be found in the mouth or GI tract can contaminate scopes. And you got to pay attention to all of these surface level defects, because those are where bugs like to hide. And typically when people are coming in for TE exams, it's because they have some underlying issue. It's not just for fun, so they're already at risk. Getting to the meat of this, I apologize that I know I'm running over a little bit, maybe too verbose here. What is an electrical leakage test? So you can see in this picture, you have a connector that is for the ultrasound probe, connects into the electrical leakage connector. That gets connected to your electric leakage tester. And then from the electric leakage tester, you have a conductivity probe that gets submerged in the conductive, either water with a salt bath or in disinfecting fluid. You can make a measurement. Most of these devices will actually make a reference. They'll put a reference voltage into the fluid, ensure that you can actually conduct a test accurately, and then it will run through a test, produce a value that will indicate that the probe passes or fails. Again, make sure that your device actually has the specific limits for the transducer that you're testing. Otherwise, you're kind of wasting your time here. So leakage is measured in microamps, and it actually tends to be used with a method that is actually safe for you to use. The device that we manufacture, as an example, it has 500 microamp limit. So if the device goes above, measures above 500 microamps, it cuts out. So if you had your finger in the water, you would be safe. I still don't recommend that you do that. Ensure that you understand what the acceptable ranges are, because those do differ by model. And when electric leakage testing is strictly pass or fail, that is not a great solution. You want to actually have the specific values, how that probe is, what that probe is measuring, because if you're passing at 99 microamps and it's trending, the last three measurements have been 90, 95, 99, you want to pull that device from service and get it repaired before it actually starts failing. Also, pass or fail devices tend to not have this display. You want to make sure that you actually know what the value is, so that you know that it's being tailored specifically to the device that you're measuring. This presentation will be available after today. Obviously, you can always watch it again, and I apologize that I've run a little too long in areas that aren't maybe aren't as focused on what we're here to actually talk about. So spend a little too much time laying the groundwork here. But if you read through each of the manufacturers, they give instructions for how often you should test the probes, what you should be looking for when you're doing inspections, and ensuring that your team knows how to actually do these properly is available for whatever specific model of probe you have in your facility. So often this testing you also need to do while it's attached to the system, but what we're talking about is a test done independently of the system typically, and that is correlated to those measurements that you would do on the system, so that it's real world. It is a good example of what you would see if that probe was hooked up to the system and inside a patient. That's the real purpose of that electrical leakage testing, is to ensure that we're not gonna hurt patients. There are underlying regulations, both in the United States, Canada, in the EU through the MDR, that outline how this testing needs to be done. You should know if your device actually conforms to that specific nomenclature and those requirements. And those are by the International Electrotechnical Commission, the IEC, and generally those have been harmonized across the world. So you do have good agreement on how the testing should be done, even if specific limits for an individual probe can be different. There are absolute limits over which they cannot go and still be used, regardless of what the particular OEM says about their device. Those are tend to be at 175 microamps. Here, again, we're looking to make sure that you actually do review the guidelines and practices. AMI is a good resource. Device IFUs are an excellent resource. So if you want to look at AORN for processing to ensure that your leakage testing is being done according to the industry best practices, those are great resources to utilize. They'll also have good information about what preventive maintenance you can exercise, and then again, of course, ensure that you're following all the cleaning steps for cleaning and processing and ensuring that the electric leakage testing is done properly. So let's see. Documenting training for all of your team members, ensuring competency for all of your team members is of critical importance. Making sure that the testing that they're doing on an ongoing basis is going to satisfy those requirements. And then obviously you're going to retrain if people aren't meeting those competency requirements. So I know I covered some of the few slides there at the end rather quickly. I'm told the platform's going to cut us off shortly, so I'll try to answer questions here in the end. What I've gone through is talking about some of the importance of electrical leakage testing, what an ultrasound probe is, how it makes images, and how to perform an electric leakage test. Be sure to review your IFUs. That is often the best place to go to get good information on these scopes. There are references here at the end that you can review. Some of them are papers that we developed. Nicholas, asked the conductivity testing. So actually, conductivity and electrical leakage testing are used often interchangeably. So we're talking about the same thing in looking at that. Sometimes manufacturers will recommend an air leakage test. That's different, but than what we're discussing. But yeah, the Astra TEE is one automated disinfecting solution. Conductivity testing or electric leakage testing does happen in those devices. You can the devices all have a standard connector, so you can use our device in place of the BC device. And where ours is different is that we do provide the actual value. You can set limits for your specific transducer within your hospital, and all of that data is recorded automatically. So you're able to actually track that over time. You're able to store that and share that easily with Biomed. So in my device, if the probe fails, you can have an email automatically sent to the biomedical engineer to be able to help you resolve that issue. So I hope that answers your question, Nicholas. If I haven't, please let me know. Yeah, Lisa, that's an excellent question. So I can't speak to all the devices on the market, but the my device actually, and I'm sure the others are similar. They'll run a test when you first turn the device on, and prior to subsequent tests. The device itself will put a test voltage into the water, ensure that the water is properly conductive, and that the device is functioning properly. Excellent question. Thank you.
All right, Levi, thank you so much. That was a lot of really good information. I've definitely needed some education myself on just the intricacies of the probes and just the steps that follow the cleaning and then electrical leakage testing. So really appreciate it. For those of you out there that have more questions for Levi, feel free to reach out to him via LinkedIn or through his email. His bio and his information, contact information is all there on the right side of the screen. He would love to answer anything related to Astatera products, or more importantly, just the intricacies of these various devices and the importance of electrical leakage testing when it comes to patient safety. So Levi, thanks, my friend. I appreciate you jumping in with us. It's been a real pleasure. Also, anybody that's looking for CE, feel free, make sure you stick in for the conclusion of this, and you'll be automatically directed to the quiz, and then you can obtain your CE certificate. So thanks again, everybody. Thanks, Levi. Thanks to Astatera Laboratories, and we'll see you all soon.